What the fuck were we doing? Alright, okay, we have a car. It goes boom boom. Like this.
Are you sharing your screen?
Nope. Thank you.
Are you recording?
Yes. Thank you.
Cool. You're welcome.
What do you need to remind me? I never forget. Never forgotten to record in my life. Okay, so I'm going. It's like boom boom boom. Of course, it's still more like a hover car more than an actual vehicle, because we can like turn when we're standing still, which doesn't really make any sense. I think we're supposed to like turn more as we're going faster. I think that's how it works. When we're standing still, we're not supposed to be turning at all. Yeah, let's do that first. So let's do it. So when we turn, we're supposed to be turning based on how fast we're going, right? Because if we're turning, all we're doing is like pointing the wheels left, right? But that doesn't actually make us go anywhere until we actually start moving forwards, and that's when the wheels start rolling to the left and we actually start turning. So yeah, we shouldn't be just applying a turning force all the time. We should only be turning based on how fast we're going. And it's good that we have our parallel velocity, because that's actually the only velocity that will turn our car, right? Because if our wheels are turned, you know, like this, we only really want to consider the velocity as pointing forwards, because that's the velocity that's gonna make the car's wheel roll. The wheels aren't really gonna roll as we're going downwards like this, or they kind of will. But for our sake, for this purpose, I will only consider the forward velocity to figure out how much we should be turning the car based on our how much we've steered. It's a good thing we have it. So I will do another section here. I'll call it steering. So we want to figure out our parallel speed. And I'm actually not gonna take the size of this. The reason is, if we're going backwards, we actually don't want to rotate in the direction the wheels are pointing. We want to rotate in the opposite direction, because the wheels are gonna move backwards. So as we're moving backwards, we're gonna turn in the opposite direction. So we're actually gonna take the speed, not the absolute speed, so not the magnitude of the vector, if you will. We're instead gonna take the vector's length as compared to the forward vector. So we're actually not even gonna use this parallel velocity. We're actually gonna do just this step here, because this step here gets the magnitude of the velocity that's pointing in the actor's forward vector with forward and backwardness considered. So if velocity is pointing backwards, then the dot product will actually give us a negative number. So we're just going to take this equation here and use that to calculate how much we should be steering.
Quick question. Right now, if you just press the left or right button, will the car turn, or does it need to drive forward or backwards at the same time?
No, it will always turn, and that's what we're trying to fix right now.
Yeah.
So that you have to actually go to turn the car. So parallel speed will be, I will dot product the velocity. I could take the parallel velocity and dot as well, it doesn't really matter, but this is always good to keep the two equations separate. So please dot product the velocity with the forward vector, and that will give us the speed, and it will also give us the sign of the speed. So it will tell us if we're going forwards or if we're going backwards, because that's what the dot product will give us. If the two vectors are pointing away from each other, then the dot product is going to be negative. If they're pointing parallel with each other, or not parallel, but in the same direction, within 90 degrees, then the dot product is positive. So now that we have the parallel speed, we can take that into account for our turning speed. So I'm gonna do 90 times parallel speed times turnaround input times delta time. Alright, so it's the whole equation. So we're gonna do 90 degrees times how fast we're going, forwards or backwards, which means if we're going backwards, it's gonna be negative. We're gonna be turning in the other direction. Times what our input is. So that's gonna be how the wheels are turned right, left, or right. Times delta time.
You know what they say, right, about big wheels? They keep on turning.
Is that a reference?
Yeah.
Oh, sorry, I don't.
Big
Oh.
wheels keep on turning.
If you don't press any buttons, where will the velocity be pointing?
If we don't press any button,
Yeah, if nothing is pressed.
then the velocity will just be whatever the last velocity was. So if we had velocity before, we'll just be slowing down. So the velocity will be like pointing in the direction we were going, but it's getting smaller. Oh! Okay. So... Okay, so now it's kind of snapping. So that doesn't seem very good. As you can see, the kind of... This doesn't really look like what we kind of want. And of course it's way too big, because we're doing 90 here. And we're timesing it by the parallel speed. But of course the parallel speed is in units per second, which is quite a big number. Like if we're going... I think our max speed is like 200. So we're going to do 200 times 90, which is going to be a huge number. So we're either going to have to do some sort of conversion here to say like, okay, we're going to turn 90 degrees per 1,000 units traveled or something. Maybe that's the best way to do this, actually. I'm just going to divide this dot product by 1,000. So for every 10 meters, I want our car to turn 90 degrees. It's kind of an arbitrary value, but it's fine. Whoops. So now I'm sort of scaling this down a lot so that when we're going at 10,000 speed, that means we're going to turn 90 degrees per second. Oops. So let's see. I didn't go down. Did I do 1,000 or 10,000? I did 10,000. Okay. Okay. Let's compile again. And... okay, so I think 10,000 was way too much. I don't think that's actually 10 meters. That's actually 100 meters. So now will be, when we're going 100 meters per second, we're turning in 90 degrees per second. So that's way too much. Let's take it down to 100 maybe. No, not 100. 1,000. Let's do 1 0 off. Okay, that's better. Still very, very slow. So I'm gonna tweak this value a little bit more. Let's do 100, yeah, sure. Oops. Okay, so that looks pretty good. So now as I'm going, I can turn like this. But if I stop, then I can't turn the car anymore. And of course, when I back, I'm sort of turning in the way I'm directed, like the direction I'm expecting. Whereas if I turn back and hold right, the car will steer to the left like this. So that's what I expected. And again, since our frictions are so low, it kind of looks like we're always drifting right now. Just, I think it's pretty neat, I guess. All right, cool. So now our steering works more like we expect. So that's cool. So that's like we're driving a car on ice. Let's add some collision, shall we? So let's say if we add some boxes or something, make a little map. We want to be able to collide into those boxes, and our car should, stop or bounce off of it or do something interesting. So let's do that. So I'll make a little level. Let's add a cube. I'm a level designer, by the way, so I'm just gonna make a little cube like that. So I'll clone that, rotate it around like this. Clone that. It's gonna be a really tiny level, but it's fine. Make a really big box. It's the worst racetrack. Whoa! I hate level design with every fiber in my body, by the way. I should say that. I despise level design. The level design courses at school, which I had to do because I went design and not programming, because programming didn't exist back then. The level design courses, I was like went up to Short and was like, please, Short, let me not do this. Like, please, I suck. just give me a G. And usually he complied because I think he doesn't care. He doesn't care if I'm gonna become a level designer or not. This is a level. La 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 la. This is how you level design. So I'll do. Yeah, like that. This is a big ass cube, and drag it out here, and God, I'm sweating. And then I'll drag this down. Whew, all right, cool. Level done. All right, sweet. So that's our level. Looks pretty sick. So right now, if we drive around, I can of course just go straight through the blocks here. Yeah, because we're not doing any sort of collision checking at all. So that sucks. So I think the first part of doing this is that we stop at the wall, right? So at least when we hit the wall, we don't go through it. We sort of stop. I think that's like a good first draft of movement. So I am going to first of all, I'm gonna add a collision to our car, because right now we don't have any collision. We have the mesh, but we kind of want to have something like controlling code. So I'm gonna just add a box collision. No, in a box component. So a box component is just a box collision. That's it. Box. Sure. Like so, and I'll make that the root component. Since we're going to be sweeping, we need the root component of our actor to be the collision we want to sweep with. So I'll forward declare it there, and I'll include it here. Fucking, there we go. Cool. So now we should have a box component on our car. Let's compile and check out the blueprint to see that everything went okay. We are gonna do ramps actually at some point. Vertical collisions are tricky, to say the least. But I'm thinking at some point we'll do like a sick jump or something. It's like BJ. BJ stands for big jump, by the way. Something else. So I'll remove the scene component. We don't need that anymore. So I'll remove that. And I'll just tweak the box size to cover our car. Make it small. Make it snug. We could have also made it so that the car collision is the thing we used, so we could have like added a static mesh as the root component. Could have done that as well. Like so, I think, and I'll move the car down a bit. Oh, I need to turn up snapping. Oops. Just move it down a little bit. Okay, there we go. I think that it's roughly fitting. Something like that. Cool. So now they're in the ground a little bit, because the center of the box is the origin of the actor. So I'm just gonna move it up a little bit. So they sit on the ground like that. Cool. So let's see what happens now. Nothing, because we of course haven't set our box to be blocking, so we gotta do that. So I'll use set the box set collision profile name to be block all dynamic. Oops. Whoops. Like so. Whoops.
Won't block all dynamic just block like every single movable object? Or would it also like block like walls, static objects?
Well, block all dynamic means block everything, and the object type is dynamic.
Ah, cool, nice.
Yeah. So it will still block everything. It would just be of type dynamic because our car is gonna move. So I'm gonna compile that and make sure that the profile got updated properly, because sometimes it does not. So I'll take a peek. Nope, it did not, because it marked this as overridden for some reason. So I'm just gonna reset the defaults. There we go, and now it's block all dynamic. Good to double check. And let's see. And no dice, because of course, even if we have a blocking, we still need to sweep to get the blocking to actually do something. So we still need to sweep our move, because now we're just doing add actor world offsets. But we of course want to sweep so that we can react and stop at walls and so on. So in the tick, in the add actor world offsets, I'm gonna make sure that we sweep this bad boy. So B sweep, I'm gonna set that to true, and then I'm gonna feed in and hit result pointer, so we can get the result of the hit if we have one, like so. Cool. Let's see what happens. So I'll play, and boom, we get stuck. So the car doesn't go through the wall. Of course, it's not like really working like I want it to work. I don't want the car to get like fucking stuck. Like, that's not very fun. I of course want the car to like bounce off the wall or something, or at least slide against the wall. I guess we can start with that. Like, how do we make the car at least slide against the wall instead of just stopping dead in its tracks? And the way we're gonna do that is that if we look at the hits,
project vector, right? Something like that.
Yes, we want to project the vector onto the plane. So if we have our car here, here's our car. Room Room is going forward. Here's its velocity. Here it is. And then it hits a wall here at some angle. So it's like bang, and here's the normal of the wall. What we want to do to have it slide along the wall is that we want to kill all velocity that was pointing towards the wall. So we want to kill all of this velocity right here. So this is parallel to the wall's normal. So we just want to basically get rid of that. So we're going to take our velocity minus this parallel velocity, So minus that. Nice n. And then what we'll end up with is going to be this. So this is going to be the velocity after the wall hits. The velocity is going to be pointing along the wall, so we are sliding against the wall rather than going into the wall. So let's do that. So let's see here. We'll do collision handling. So if we have a hit, then, whoops, then we will constrain our blocking or velocity against the wall. So we'll do, we'll make a vector called like impact velocity. And that's gonna be the velocity that is pointing towards the wall. And how do we get that? How do we get the velocity along this normal?
Dot product between normal and velocity.
We should be able to just get the normal from the object that we hit, like the hit point normal.
Yeah, so we'll do exactly. We'll do a dot product. Of the velocity dot the hit normal. And that's it, nothing else.
Shouldn't we like reverse it, the normal?
Well, are we done here? Are we done with this line here?
No, we're gonna want to take that times the normal.
Yes, exactly, because we still wanna we wanna get it as a vector. This will only give us the length, like how much of our speed is pointing towards the wall. But we still wanna get it as a vector, so I'm gonna times it by hit normal. And this will give us the velocity projected onto the hit normal. And then what we can do is that I'm just gonna do velocity minus equals impact velocity. So that's we're sort of taking the impact velocity out of the equation. So the only velocity we're left with is the one that's pointing along the wall. Cool. So let's see if this works. I'm gonna go and take him to speed. And let's go, baby! Whoa! I haven't compiled. So this compile. Okay, there we go. Okay, so there we go. Okay, so just build up some speed and let's go. Okay. So it kind of works. Like it's sometimes I'm sliding. I slid for like a few frames. Well, the problem here. The problem here is that sure, this works. This does work. The problem is we don't finish the frame, right? We just move and then we stop for that frame, and we don't move anymore. The problem is what happens the next frame. The next frame before we move. So let's say like, okay, here's the, oh shit. How do I redo? Oh, there. Fuck. Okay, here's the wall. So this is the end of the last frame, right? Our velocity is pointing straight, God snapping bad away from the wall. So we should not be hitting the wall right now. Problem is, next frame, we're still holding down the accelerate key, which means we have an acceleration this way. And even though it's tiny, like it's not like we're gonna fucking go like crazy, it's still gonna twist. This is gonna twist this velocity. It's a tiny antsy bit back towards the wall. So we might the next frame have something like this, like it's pointing just a little bit towards the wall. And what's gonna happen the next frame, or rather this frame, like, so we apply the acceleration, so we're pointing just a little bit towards the wall. What's gonna happen is as we move, we hit the wall right away, because we're right next to it. So even though it's only pointing a little bit towards the wall, we are right at the wall, which means that even if we go a little bit forwards in towards the wall, we're gonna be hitting it. So then the same thing happens. It removes the velocity, so we're back to having, you know, velocity perpendicular to the wall, but we don't move. The next frame, again, same thing happens. We add a little bit of acceleration. We go a little bit towards the wall. We crash with the wall. It goes back up and so on. So we're stuck in like a loop here. We're never getting anywhere. So the way there's there's a lot of ways to do this, to fix this problem. We could add a bounce, for example. So we could say like, okay, instead of only going straight there, we're actually going to have a little bit of an impact as well. So we're going to add a little bit of an impact away from the walls, away from the wall. So instead of the velocity being completely parallel or perpendicular, sorry, we'll have like a velocity that's pointing slightly away, something like that. So we have like an impact with the wall, and that will ensure that next frame we will be moving away from the wall. We won't be moving at all towards it. We could do that. So I'll do like, maybe we add impact velocity, and then we also minus a little bit more. So I'll like minus, I would like minus like impact velocity times 0.3 maybe. So it's like we remove impact velocity, but then we add a little bit more. But like we add a little bit more velocity, like by 0.3. So that will be like a bounce. And by using the impact velocity, that means the harder we hit the wall, the harder we're gonna bounce back. So we can do this. That's one way of solving it. Let's see what happens. And we might very well do this in the end as well, because it's just juicy to get a bit of a impact, because, you know, for every action there's a reaction, right? So if we hit the wall is going to be hitting us way back as well. So I mean, in real life there would be a bit of an impact bounciness. So let's see what happens. So I go against the wall now. Okay, it's, I don't know if it actually compiled. Let's try again. Okay, yeah, so it worked better, because now as I'm going into it, you can see that I'm like sort of bouncing away from it, right? Let's try again. See that? I got like a little impact, right? So it's like if I'm hitting this wall, bang, 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 I like bounce away from it. So it seems like I can kind of keep going, right? So it's like, okay, I'm not getting stuck. I'm getting like a little push, a little love tap. So that's good. That's definitely better. However, if I really, really try to ram into the wall, I will still get stuck. Because at some point, like the bounce is going to get smaller and smaller. Like you see, it's like a big bounce, smaller bounce, smaller bounce, smaller bounce. At some point, the bounce is just going to be nothing. So then we have the same problem where the bounce is not great enough to actually push us away from the wall. So we still have the same problem where we're constantly trying to force ourselves up on the wall, which is never nice. So the solution kind of works, but it's not definitely not like a perfect solution by any means. So what we want to do is something called iterative stepping. I actually don't know if that's the right word, but that's what I'm calling it right now, iterative stepping. And what we want to do in this case is and this was like months of my life when it takes to doing this, exactly this thing we're gonna do now. We have a car, it's going, boom boom, it hits a wall. Oh no, how sad. Feels sad, feels bad, man. So it hits a wall, and it bumps off. So it's like, as it bumps off, we redirect its velocity. So its new velocity is going to point somewhere around like here. So that's going to be its new velocity. The thing is that the frame is not over, perhaps. Let's say that, you know, okay, we were gonna move from here to like here or something. Like that was gonna be our frame movement. But we sort of got stuck in the middle. Like we hit it, and we hit it right here. Here's where we hit the wall. So we didn't finish this movement here. So what we're gonna do is that we're gonna redirect this final delta movement. We're gonna do the same thing that we did with velocity. We're gonna constrain the delta movement. We're gonna constrain that in the exactly the same way, like this. And then we're gonna move that distance. So we're gonna iteratively keep moving until we ran out of delta to move. So we're gonna, like, finish the delta, even though the delta, as we keep going, will sort of change. So we might hit a wall, and then we need to, redirect the delta, because, we hit the wall, we can't go there, and then keep moving until we finish the frame. So this is very common. This is like, the solution in almost all collision, like character movement and so on, is that you wanna keep iterating on the delta. Like, okay, I move out, I hit the ceiling, and I also hit a wall, and you keep doing these iterations until you've actually finished the whole delta frame.
But wait, so what's the difference then between like pointing our velocity vector alongside the wall and what you're describing?
The difference is if we use point the velocity, because we are going to do that as well. We are pointing the velocity, but we are sort of disregarding this last part of the delta. We are not moving this part that we should be moving.
Like.
So we're not moving as much as we should have moved that frame. Because think about it, if I'm the car, right?
Yeah.
And 1 second passes, I'm expected to move an amount of units in 1 second. Right?
Yeah.
If I'm going 100 meters per second, then I'm gonna move 100 meters. If I hit a wall, my speed might change, right? So it is like, okay, I hit a wall, so my speed went from 100 to 50. But it's still a second, it's still gonna pass. So I'm still gonna have to move that second's worth of movement. Even though maybe half of it was 100 meters per second, and then the second half of that second was 50 meters per second. I'm still expected to move the entire distance. It's not like I'm gonna walk for 0.5 seconds and like, oh, I hit a wall, I'm done for this second. Like, I'm still gonna have to, no, you have to keep moving. Like, it's like, you can't just wait for the next second to, okay, now I'm gonna keep moving. And that's sort of what happening here. In the middle of the frame, we hit a wall. But there's still movement left to be done. Like, if you think about it in like time, so if we like split up this frame into like a timing sense, then the car is sort of moving like this, and bang, it hit a wall. Like, if sort of integrating the frame in our heads. But half of the frame has only passed. There's still half of the frame left to move. So then we want to figure out, okay, how should we move for the rest of the frame? And that's why we're redirecting the final delta and saying, okay, here's the final delta after the hit. That's where we can move. And then we move that final bit. So then we will actually finish the entire movement for this frame. We've extended the entire second of movement instead of going halfway, hitting a wall, and just stopping.
Also, something worth noting, like, I was really confused about this before I realized that we're sweeping and not actually, we're not triggering it when we actually hit the wall. We're just triggering that we're gonna hit the wall if we do this movement, right?
Yeah, you can say it like that. In It Takes Two, like, we don't actually move the player at all. Really, we only like sweep like a dummy collision, essentially, like a fake collision. And we like try everything out, and then at the end we're like, okay, you should have ended up here, and then we just teleport the player there.
Oh.
So I mean, it doesn't really matter. It's sort of the same. It won't matter in this case. In this case, we are like actually like moving up the car, and I'm gonna go, move the car a little bit more. But in the end, it's the same. Because in the end, like in this case, maybe it's a little bit vague what this means. Because in this case, it's not really broken because we have moved forward. But the case where this will save us, where it won't be broken at all, is the case where we have a little bit of force or a little bit of velocity towards the wall, but most of it away from the wall. In this case, where the velocity is pointing slightly inward. What's gonna happen here is that we're gonna get a hit almost immediately, like almost like second 0 of our frame. It's like psh, we hit the wall. So it's like, okay, I'm gonna start my 1 second. Let's say like a frame is 1 second, and I'm like, okay, I hit the wall right away. Like I didn't even get to move. I still have velocity. Like I'm still supposed to be moving. So we're gonna redirect like where I'm gonna be moving. And it's like, okay, my timer says like 0.001 second, and I have to move 1 second. So then I'll move the rest of the second in the redirected direction. Without doing that, what's gonna happen is like it's gonna be like hit the wall immediately and be like, can't move. Seconds over, I have velocity, but I'm just gonna ignore that velocity for this frame for some reason. So it's gonna be like a stutter frame where you just don't move on that frame for some reason. I hope it kind of makes sense.
Yeah, I think I get it a little bit more now.
Yeah, it's fine. It's fine if it doesn't feel super intuitive. Yeah, super intuitive. But that's what we're gonna do. So let's see here. How should we do this? Let's do a time warp again. Let's do. Right, so let's make a variable. That's f vector delta to move. And that's going to be velocity times delta time. So as you know, in the beginning of the frame, this is how much delta we should be moving this frame. Cool. So we move, and I'm gonna move delta to move. Like that. And then we have a hit. Oh no. Oh dear. We had a hit. Now we need to figure out how much of the delta did we move. So you know, in the case of we went up to the wall. Here's our car. We started here. We were supposed to go here. Here was like the delta to move, right? But we hit the hot wall here. How much of the delta did we actually move? This part. What we want to find out is how much delta is actually left on this frame. So we want to shave off this bit here before we continue. To say like, okay, we actually did successfully move this part. Take that away. And hit has a very nice, convenient variable in it. It has time. Oops. And as I said before, time is a floating point, which is from the start to the end, where the start is 0 and the end is 1. How far did we get into the trace before we hit something? That's what time is. So if we hit something right away, it's going to be 0. If we hit something at the very, 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 very end, then it's going to be 1. And if we hit something in the middle, it's going to be 0.5 and so on. So in this case, it would be like, I don't know, 0.7 or something. Because it seems like it's roughly 0.7, like 70% of the trace got done before we hit something. So it's pretty easy. We can just take away. So I'll do delta to move. Whoops. Minus equals delta to move times hit time. Right? Because this part here, that's going to be delta times time. because we're scaling delta by how far we actually went. So in this case 0.7, we will scale delta by 0.7, we get this part, so we shave that away from the delta. So it's taking delta to move is minus equal delta to move times hit time. Very good. Then we do the constraining. So I will constrain the velocity, so I will do the velocity redirection, but I will also do that on delta. So I'll do delta to move minus equals, or maybe I'll do the constrain. It's like project onto what's the difference? Vector plane project. I guess I'll do it myself. So I'll do delta move is equal to or minus equals, sorry, f vector colon dot product. I'll just do the same thing as I did with velocity. Delta to move hit normal. Fuck it, god damn it. Times hit normal. There we go. Same thing here. I'm taking away everything from the delta that was pointing inwards towards the wall. So I'm taking this delta here and just like whoop, shifting it up like this. And this is the delta we're left with. So now that we have the delta that's parallel to the wall, or perpendicular to the wall rather, we can continue moving this. And it's important that we take the remainder, because if we only redirect the delta and move that, then what would happen here is that we would move 0.7%, we would redirect everything, so we'd get like, you know, something that looks like this. Like that, I'm taking the whole vector here and projecting it onto the wall. If we move this part now, then we will clearly move a greater distance than what we like intended to do from the initial delta, right? Because if I add this big boy to the end here, like we're gonna move from here to there, which is clearly way longer than just this initial delta here. We only want to move, okay, what is left of the delta? What didn't we move? We want to keep moving in that, with that delta. Cool. So now we have this remaining delta here. Let's constrain to the wall. And now we're just going to sweep that delta. So let's sweep it. I guess I can set it in the hit as well. It's fine. Reuse that variable. Like so. So we're taking the remaining delta and moving that delta forward again. Pretty sick. What the fuck could go wrong?
We can just end up stopping if we're at like a 90-degree turn.
Yeah?
Because we want to use the delta to move like a resource until it's reached 0, right?
Yeah. That's true. So let's see here. Okay, so if I bounce against this wall now, let's see what happens. Nice. Okay, so we're sliding against the wall. Because every frame, even though our acceleration is pointing inwards towards the wall, we are considering that, and we're taking sort of the remaining delta after that little tiny baby impact and still using that to move. Problem is, of course, if I'm going into this corner here, you can sometimes see that it's bugging out a little bit. Let's see if I can get this going. It will sort of be like one frame of stopping, I think. And why is, can anyone see when we're sliding into another wall, can anyone guess why that would maybe cause some problems?
Because when we're moving with the remainder of the delta move, and it hits another wall, so say it hits the first wall, we redirect it into another direction, and it hits a wall again. We don't have anything that checks that right now, so we just end up stopping.
Yes, exactly. So if we are sliding against a wall, we have already done the redirect, but then guess what? There's another fucking wall right here. And we hit that. Then we don't do anything. Then we're back to square one, where, we're just stopping against the hit. And this is why it's called iterative collision solving, because we want to iterate more than once. We're iterating once now, but we want to keep iterating until we're left with no delta at all. So, we want to go like, okay, we hit the wall, bang, bang. Okay, see how much delta is left. Again, redirect that little tiniest delta, bang, bang, and keep moving until we've ran out of delta, because then we've moved. Yeah, like you said, it's like resource. We got this big chunk of resource in the beginning, and we sort of shave them off with every iteration, and then we keep moving until delta is gone. So let's write that. It's not that hard, but first let's take a 10-minute break. So this was a math-heavy segment, so I need your brains to cool off before we finish this epic saga.